Greetings again. This is Mr. Glenn of ACT Prep Chicago. Um, we're doing a answer explanation for ACT Practice Test 2, which can be found via the ACT Direct website. I think there's a link in the description for the video. Um, this one here, ACT Practice Test 2 PDF. I believe it's the same questions as if you scroll down to the digital version of the exam, which would be called standard version of the new enhanced to-do version, practice test 2. And we're going to do the science section today. Science section. Um, yeah. So without further ado, let's get started. The science section is all the way at the bottom, the last section of the exam. Um, for more assistance, if you need more assistance with any questions, you can reach us at actprepchicago@yahoo.com. Send us an email. More than happy to offer some assistance on the question. Um, and if you're interested in tutoring services as well. All right, without further ado, so with the science questions, we go straight to the questions. We don't read the text. If you try to read the text, charts and graphs in advance, um, you will not be able to come close to finishing the section. So that's just a strategy. But this is not about strategies. This is really just about reviewing the answers. So those who may um, take the tests and who looking for some explanations on each question can have a video version. You can probably put in AI and get a written version, but this is a video version that could be more assist to be able more assistance. Okay, number one, according to table two. All right, so we do a lot of back and forth. Illustrated question. Table two. Here's table two. All right, what about table two? At 1 ATM, that's not really on there. Well, if you look above the table, it says MP at 1 ATM, BP at 1 ATM. So MP usually stands for melting point, which is probably at 0 degrees, and BP stands for boiling point. If it's not sure, you can always look for the first mention of it, which is here. You see MP in parentheses, melting point, BP is boiling point of different, I guess, substances, right? All right. What is the BP boiling point of the alkaline with chemical formula C5H10? So C5H10 BP is 49 degrees Celsius. Answer to D, I mean, the answer to number one is D. Okay, moving right along. Number two. For the N-alkanes listed in table one, ill alkanes listed in table one, that's these, I guess these are the N-alkanes. As the number of carbon atoms per molecule increases, so you might have to know some background information about this, because I don't think they mentioned number of carbon atoms, or how to look at them. So you do have to know a little bit of background information. Um, And this is a molecule, right? And it's when you mix atoms. So we mix in carbon and hydrogen to make this chemical formula for propane. But it has 3 carbon atoms and 8 hydrogen atoms. So that's just how you read that. So as the number of carbon atoms per molecule increases, so C3, C4, C5, C6, C7, C7, as we're going down the table, you see how the number of carbon atoms in each molecule increases. The BP does what? The BP goes from -42, -136. It also increases, right? Now be aware that a negative BP going closer to zero is an increase, even though it looks like it's going down. Remember, that's negative. So this is all increasing. So increases only. So number two would be F, increases only. Okay, number three. At 1 ATM, how many of the cyclocanes, I think that was table two, right? This in table two, have an MP above the MP of ice. What is the melting point of ice? So let's see if they give us the melting point of ice. They do not. They do not. I do not see. melting point of ice. So what do you have to do? You got to know what is the melting point of ice, which essentially is water, right? So water becomes a liquid because that's the melting point, right? So when does ice become a liquid? That's the melting point. That's when it starts to melt, right? So it's 0 degrees Celsius is the melting point of water, right? Or melting point of ice, right? Or you could say it's the freezing point of um, water. So it's both, right? If you go from water to ice, you're freezing. If you go from ice to water, you're melting, right? So 0 degrees Celsius. So we're asking how many of these have a melting point that is above 0 degrees? Well, we got here 7, 15, and 11. So it'd be 1, 2, 3. So it requires outside information to get that question. The answer to number 3 would be B, right? Based on table 1 and 2, yeah, I should check that one just to make sure. But I should have been checking all. Well, I don't have to check some of these. They're so easy. Um, 2 is F, 3 is B. I just want to see 2 F, 3 B. Science. Yeah, 2 F, 3 B. Yeah. Uh, guess I could. I'm not, I don't do that for science. What was that? That was number 3, 4. Based on table 1 and 2, so we got to look at both of them together. So typically, when you have to look at two together, you're looking at what they have in common. What is the name of the N-alkane shown in Figure 1? Where's Figure 1 here? N-alkane shown in Figure 1. And what is the name of the cyclocane shown in Figure 1? Okay, so Figure 1 has 1, 2, 3 carbon atoms and 1, 2, 3, 4, 5, 6, 7, 8 hydrogen atoms. So we can C3H8 should be propane. So the name of the N-calcane, which is table 1, will be propane. So it's either F or G, right? It's not butane. And then what's the name of the cyclocane? For figure 1, it has 1, 2, 3 carbon atoms and 6 hydrogen atoms. So that would be cycloprane, cyclopropane, which would be F. So number 4 is F. All right. Number 5, based on table 2, in a molecule of any given cyclocane, the number of hydrogen atoms is always equal to, so we're comparing the hydrogen atoms to the carbon. Half the number of carbon, the number of carbon, twice the number of carbon, 4 times the number of carbon. So based on table 2, how's the number of hydrogen atoms compared to the number of carbon atoms? It looks like the hydrogen atoms are twice the number of carbon atoms, 2 times. So the number of hydrogen atoms is always equal to twice the number of carbon atoms. That would be choice C. You can see here, like what? Hydrogen is 6, carbon is 3, that's twice. Hydrogen is 8, carbon is 4, that's twice the number of hydrogen atoms. Hydrogen is 10, carbon is 5, that's twice the number, and so forth. All right, hopefully you can see too from doing these exercises that again, you don't have to have really understand this passage to do well and you don't have to read it in advance, right? You don't have to read first. Especially when you got tables, charts, and graphs. Now the second passage, it looks like this is going to be two things. I went over that fast. The first thing is you don't have to be a science expert to do well on this. Two, you don't have to have read and fully understand what this experiment is about. As you can see, I answered all of these questions without really a full understanding of the experiment. Okay, I still don't know if I had to write an essay on the experiment, I still wouldn't be able to do so, but I can answer questions. So that's the power of going to questions first. I'm giving you cats a lot. This is normally what I do in a one-on-one tutoring session. However, let's move on. So now with this passage, though, this is different. Why is it different? Because it is what we call a conflicting viewpoints passage, and it does not have any charts, graphs, or tables. It's essentially a reading passage in the science section. It's the only one like it. But these passages you actually do read first because, like our reading section, you want to get an idea of where stuff is and what's being said so you know what to look for. It doesn't have to be a hard read, just an overall what's happening read. Because remember, it's open book test. You can always come back to the questions for the details. All right, but I like to read these first actually instead of going straight to questions. So star formation begins with the gravitational collapse of matter in interstellar gas cloud. Gravitational collapse. A protostar forming star affects gas in the surrounding portions of the cloud in two ways. So a protostar forming star affects gas in the surrounding portions. The protostar's gravitational field attracts gas, causing the gas to accrete, accumulate onto the protostar. Radiation pressure associated with the protostar's emission causes gas to be pushed away from the protostar, inhibiting accretion. Now, so these are opposing things. So gravitational field attracts the gas, radiation pressure causes gas to be pushed away from the protostar. So they like opposing. Star formation ends when the effect of RP overcomes that of gravity. Okay, so that's because you're not attracting any more gas because radiation pressure is pushing away more gas and is being attracted by gravitational field. So that's what they say. RP overcomes the effect of gravity. At that point, the protostar can no longer gain mass by accretion. That makes sense, and is considered a fully formed star. Three scientists debate whether the maximum mass that a protostar can reach by accretion is great enough to account for the most massive stars observed. Scientist one says the effect of RP is uniform in all directions around a protostar. Effect of RP is uniform, the radiation pressure. That means you're pulling away gas from the star. As a result, the maximum mass that a protostar can reach by accretion is 20 ms, and ms is mass of the sun's, the 20 masses of the sun. So it's pretty big. So you put 20 suns together, they say that's the largest size that a protostar can reach. Any further increase in mass requires at least one stellar merger, a combination of two or more fully formed stars into one. So accretion can only get up so big, right? If you want bigger than that, you have to have two big stars coming together. I guess it's different because stars tend to form a cluster, stellar mergers are likely. All right, scientist two says scientist one is correct that stellar mergers are likely. However, because a protostar rotates about its axis, a disk of gas forms in the plane of the protostar's equator. This reduces the effect of RP in that plane, allowing gas from the disk to readily accrete. As a result, the maximum mass that a protostar can reach by accretion is 40. Any further increase in mass requires at least one stellar merger. So it's saying the same thing, except for scientist two is saying that the protostar can reach a larger mass, 40 as opposed to 20, like double the mass, by accretion. But then after 40, then you need a stellar merger. So scientist two basically says accretion allows for a larger starter form. And then scientist three says stellar mergers are very unlikely. Also, this one says no stellar mergers are happening, given the vast distances between stars, even within clusters. Scientist two is correct, but the formation effect of the disk, about the formation effect. In addition, a protostar produces bubble-like regions of radiation that increase the effect of RP near the protostar's poles, promoting the flow of gas into the disk. But why would that promote flow of gas into the disk if radiation pressure pushes gas away? As a result, accretion continues until the surrounding portions of the cloud are nearly depleted of gas. Therefore, the maximum mass that a protostar can reach by accretion is limited only by the amount of available gas. So this place says, as 3 says, there's no limit on how big a protostar can get based on accretion. All right. So 1 says it's 20 mass of the sun, 20 MSs. 2 says accretion can make it 40, and 3 says it's depending on how much gas is around it. So it's infinite how large protostar can become based on accretion. But so since 3 also says stellar mergers are unlikely. Okay. All right. Relative to the center of the protostar. So that was good. So that's why you read overall, because when you read overall, you can understand each other argument better because you get relationship between each other. All right, number 6, relative to the center of the protostar, does gravity more likely accrete gas particles inward or outward, and thus RP more like a accrete gas particles. So gravity attracts. We read that. So gravity would be inward and RP would be outward. That would be G. Because it says gravitational attracts gas, causing gas to accumulate onto the star. Radiation pressure causes the gas to be pushed away from the polar star. So gas particles go outward towards the center for RP and inward for gravitation. That would be G. All right, number seven. Based on scientist two's arguments, what is scientist two? Scientist two was the one saying that stellar merger is possible, but it's you can make a bigger protostar by accretion than scientist one. All right. Do gas particles more likely accrete near the equator or near the poles of a protostar with a disk? Near the equator because the effective RP is increased there. Near the equator because the effective RP is reduced there. Near the poles because the effective RP is decreased there. Near the poles, likely accrete near the equator or near the poles. I think that was scientist three argument was talking about where accretion would happen. Okay, scientists very highly so however, because the protostar rotates about its axis, a disk of gas forms in the plane of the protostar's equator. So the disk of gas is in the protostar's equator. This reduces the effect of RP in that plane, allowing gas from the disk to readily accrete. So, do gas particles more likely accrete near the equator or near the poles? I think it would be near the equator because it says a disk of gas forms in the plane of the protostar's equator. We reduce the effect of RP in that plane, so that means the gas is not being pushed away, it's actually drawn towards it near the equator because the effect of RP is reduced there. They actually said it, they just said it, so it's B. 7B, they just said that. We read that the gas, uh, the disk of gas forms in the plane of the protostar's equator. This reduced the effect of RP in that plane, allowing gas from the disk to readily accrete. Yeah, they said it. It said so the gas is near the equator because the effect of RP is reduced there. That was B. Let me just make sure. So just like to check to see how I'm doing on some of these. Because sometimes they seem so easy, and I just want to make sure. It seems pretty easy. I didn't go far enough. That was too. No, I didn't go far enough. This is the science here. So 6 is G and 7 is B. Yes, that's correct. So I'm doing well. Just want to make sure. Okay. 8. One of the most massive stars known as ETA Carinae, which has an approximate mass of 120 ms. Based on argument scientists 120 respectively, what is the minimum number of stars, each formed entirely by accretion? All right. What is the minimum number of stars, each formed entirely by accretion, that would have been required to form? So if they were all formed by accretion, minimum number of stars, each formed entirely by accretion. If for scientist one will be 6, right? The minimum. You can have 5 essentially because scientist one says that the largest that a by accretion, the largest that a protostar could form by accretion was 20 ms for scientist one. And so how many times is 20? That's the largest. So it has to be 6 because if it were 5, 5 times 20 was 100. That wouldn't give you 120 ms. So to get 120, if the largest that scientists won is 20 ms, the largest star by a protostar that could be formed by accretion for scientist one was 20 ms. How many times is 20 going to 120? That would be 6. So scientist one will be 6. And then scientist two, if you remember what we read, the largest that a protostar can be made by accretion was 40 ms. So how many times is 40 going to 120? That would be 3. So that would be 8. Scientist 1 would be 6. Scientist 2 would be 3. Scientist 3 would be 1 because they said there was no limit to. So Number 8 is H. The scientist 3 said there was no limit to how big a star could be by accretion. So 120 ms could be the size of a protostar that was formed by accretion with scientist 3. All right, number 9. When the effect of RP, I got that from just remembering, but I don't know if you read. You see here, the maximum mass that a protostar can reach by accretion is 20 ms for scientist 1. For scientist 2, it was 40 ms, maximum mass. So that's what I did. I did 120 divided by 20, 120 divided by 40, and this was no limit to how big it could get by, how big a star could get by accretion. So we just said that was one. You can have one 120 ms star. When the effect of RP overcomes that of gravity, the star 2 is said to have emerged from its envelope because that is the first time the star is directly observable from outside the cloud. An observation of which of the following stars emerging from its envelope would support scientist U argument but weaken scientist one's. In fact, RP overcomes that of gravity. It would be support scientist two's argument for weaken scientist one's. It would be 30. No, yeah, it would be 30 because a 30 ms star is can be formed by accretion, right? Which is when, but the biggest it gets is when they said, if you read it, it said the largest it gets is when the effect of RP overcomes that of gravity. A star is said to have emerged from its envelope, or that's when it's fully formed. When do we read that? Star formation ends when the effect of RP overcomes that of gravity. That means at that point, the protostar can no longer gain mass and it's fully formed. That means it won't get any bigger, right? So if the photostar can't get any bigger, that's the maximum mass. That's when it's emerged from its envelope. Um, An observation of which of the following stars emerging from its envelope would support scientist Su's argument, that means as big as it can get, is 30. That's fine with scientist 2. But scientist 1 says that the biggest the stars can get is 20. So that means that 30 would be outside of scientist 1's range. It would weaken scientist 1 argument. If you saw a 30 ms star that was formed by accretion, right? You would say, oh, that's not possible because scientists once said the largest was 15 or 20. The reason 50 doesn't work is because scientists too, if you said a star was 50 ms formed by accretion, scientists too would say, oh, that's not possible because the largest a star could be by accretion was 40 ms according to scientists too. So 50 will weaken both scientists' arguments. 15 and 20 will work for scientist 1. It wouldn't weaken scientist 1. 30 would work for scientist 2, but it will weaken scientist 1, which is what the question asked for. The answer is C. Again, because 30 is within the range of a possible star formed by scientist two's argument, who said the largest can be 40 ms. So 30 is within that 40 range. It's less than that. So that means a 30 ms star could be formed by accretion. But scientist 1 would say a 30 ms star could not be formed by accretion because the largest star, according to scientist 1, would be 20 ms. So C would be within scientist whose arguments. It would support it, but it will weaken scientists. Okay, number 10. Scientists 2 and 3 agreed that a disk forms around a protostar as a result of the protostars. What makes a disk form around a protostar? It wasn't merger. Location within a star cluster, no. Emission of radiation. I think that was right because they said it was G. What the disk forms around a protostar. What leads to the disk forming around a protostar? I think it was the radiation pressure, right? That's what they said. They said a disk, however, because a protostar, oh, because it rotates about its axis, it just gas forms in the plane. The disk reduces the effect of RP in that plane. So it's because it rotates, protostar rotates about its axis. But actually, that would be because of the motion, but that leads to a reduction of radiation pressure. Yeah, so it would be F. The scientist three just said the same thing. Stellar margin about the formation and the effect of the disk. Yeah. So he says scientist two says scientist three, sorry, scientist three says scientist two is correct about the formation and effect of the disk. And scientist two says the disk is formed as a result of it spinning on its axis, which is motion. That would be choice F. All right, 11. Which of the son of the scientists, if any, would be likely to agree that the sun could have formed entirely by accretion? All three. How do we know that? Because scientist one says the largest that a star can be, or protostar can be formed by accretion is 20 ms, which is 20 masses of the sun. So we could do 20 suns essentially. So yeah, one sun could definitely be formed by scientist one. Scientist two says the largest that a protostar can reach by accretion is 40 masses of the suns. We know that, right? So one massive sun could definitely be included in the 40. And scientist three says that the size that protostar can reach by accretion is unlimited. So it's all three stars, all three scientists, one, two, and three, would say that the sun could have been formed entirely by accretion. In fact, scientist one would say you can make 20 suns, or you can make a star the size of 20 suns, as large as 20 suns. Scientist two would say you can make a star the size of 40 suns. Scientist three says you can make a star as big as you want. No, it's no limit on how large a star could be formed by accretion. Okay, so that would be all three scientists. All right, let us remember that question. Number 12. I'm gonna have to do this in two parts because it's just taking time. But anyway, which of the following pie charts best represents the seedling mortality results for group 4? Pie charts best represent seedling mortality results for group 4. Seedling mortality. Seedling mortality here, group 4 there, that's 6%. All right, what am I looking for about that? Which of the following chart, oh sorry, pie charts represents the seedling mortality results for group 4%. Seedling mortality. Yeah, looks like this is 6%. So if mortality, that means the rest would be surviving. This would be the completely opposite. This is wrong. This is wrong. Yeah. So if it's 6% seedling mortality, that means that all the rest are surviving. That means you got way more surviving than dying. So 12 will be F based on what I looked at, because it said group 4 seedling mortality would only be 6%. Meaning only 6% died. That means 92%, no, 94% did not die. All right. Which was F. The 13. The pots in which group were most likely covered by the greatest number of layers of the plastic mesh? Pots in which group were most likely covered by the greatest number of layers of the plastic mesh? So pots in which group covered by the greatest layers? I bet you it's group 1 because, and the reason I think that is because sunlight intensity was only 10%. So maybe the mesh covered some of the sunlight. Whereas a group 4, if sunlight intensity was 100%, that means nothing was covering it. I'm going to assume group 1 based on just looking at that chart. Let me just see about the mesh though. I just conduct a study to examine how sunlight intensity, percent of maximum possible sunlight affects seedling growth. What did they say about the mesh? In 3 of the groups, all the pots in the group were covered by the same number of layers of a plastic mesh to reduce sunlight intensity. The number of layers was different for each of those 3 groups. And wait, and the number of layers was different for you. I don't get that. But anyway, I was right. In three of the groups, all of the pots in the group were covered by the same number. Okay. The number of layers was different for each of those groups, and the layers are right to reduce sunlight intensity. So, right. So, group one had the most mesh because it had the lowest sunlight intensity. Group four had no mesh because they had 100% sunlight intensity. Nothing was keeping the sun from hitting the pots. So we'd say group one for that question. They decided like they had the most layers of plastic mesh. 13 is A. 14. Based on the results of the study, approximately what percent of the seedlings that received a sunlight intensity of 10% survived in 10 weeks? What percent of the seedlings that received a sunlight intensity of 10%? Based on the results of the study, approximately what percent of the seedlings that received a sunlight intensity of 10%? Sunlight intensity of 10%, that was group one. Group one, what about group one? Survived. So if the mortality rate was 8%, that means 92% survived. It would be H. 100% is the whole thing. If 8%, so group one had a sunlight intensity of 10%, had an 8% mortality, that means 8% of the seedlings died. That's what mortality means, which means the rest survive. So if 8% survive, the rest is 100% minus 8%, which would be 92% survive. That would be H. 15, suppose that as the plant dry mass increases, the leaf areas ratio, I measure the leaf area per gram of plant, decreases. So they have an inverse relationship. So as the plant dry mass increases, plant dry mass is here. As it goes up, the area decreases. Well, plant dry mass increase, but then decreases there. So it will be decrease, then increase for the area. It's opposite. Based on the results of the study, the plants in which group most likely had the lowest leaf area ratio, but that means we're looking for the highest dry mass, right? Because they said as dry mass increases, leaf ratio area decreases. So if we want the lowest leaf area ratio, that means we want the highest dry mass, which would be group three had the average dry mass. So group 3C. The effect of what antibiotic factor was examined in the study? Sorry, not antibiotic, abiotic. The effect of what abiotic factor was examined in the study? Dry mass, precipitation, seedling mortality, sunlight intensity. I don't know what the abiotic factor was. So you would have to know background information of what an abiotic factor or abiotic, I'm not even sure I'm saying it right. I was just giving a word to see if they talked about abiotic factor. Scientists conducted a study to determine how sunlight intensity affects seedling growth and survival. Yeah, I don't see the word abiotic here. Sometimes you'll see the word to tell you, and I didn't think that would. So this requires you to know what is an abiotic factor for that. Is it dry mass? They were testing sunlight intensity. I'm not sure if that's abiotic. It's probably not that easy though. The whole experiment was about sunlight intensity. But you really weren't measuring sunlight intensity. You were controlling sunlight intensity. You were examining the effect of sunlight intensity on how these plants grew. So maybe an abiotic factor would be seedling mortality. I bet you that's what it is. I would guess H for that one. Instead of looking up abiotic, I can just look at the answer key. And the correct answer is going to tell me the abiotic factor. What's wrong with that? Oh, man, that was question that was. I started looking at the answer before remembering the question. That was number 16. 16 is J. So abiotic factor Where's sunlight intensity? Okay, so all right. So that was as easy as I thought. So I overthought that one. Because this experiment was really examining the effect of sunlight intensity on plants. So anyway, I didn't know what abiotic factor was. Now I know sun is an abiotic factor. All right, based on the results of the study, so don't get upset at missing those because most of the questions don't require you about background knowledge. Good thing, that's a good thing about the science test. If they did, you would have to really know science. I probably wouldn't do as well on these exams, but I can do very well in these exams because all the information is here. As you can see, most of the questions, I think it was another one that required background information because you had to know, looking at a molecule or a carbon, a molecule formula, chemical formula, how many atoms, right? That's wasn't hard to do, but I did know that, but had to know that background information. Based on results of the study, what was the dry mass of an individual seedling in group two? Dry mass, individual seedling in group two. Group two, the average dry mass was 0.58, but we don't know what the dry mass was of an individual seedling. We just know once you take them all, you did the average. Population divided by four groups, and then all groups of possible placed next to each other, and three other groups are possible. They didn't tell us how many were in each group either. See, they're going for next two is pots. How many pots is each planet going identification? 800 similar sized seedlings were selected, and each was transplanted into its own pot. So 800 pots, all the pots were identical and they contained the same amount of particular soil. The pots were equally divided into four groups. So that means it was 200 in each group. I don't think that's still going to tell us, based on the results study, what was the dry mass of an individual seedling group two. We don't know that because we just know the average, right? So we know if you took the mass, the dry mass of all the seedlings in group two was 200 pots and you divide it by 200, you would get 0.58. We know that's the average, but that's not necessarily the dry mass of an individual seedling. And group two average won't tell us that. So it will be D, can determine that from your information. Okay, moving on to passage four. In each trial, the flasks were most likely shaken to. So why did they shake the flasks? Increase the concentration of B and of MD in the solution. I don't know. I didn't read the experiment. I'm just looking at the reasons before I read because maybe decrease the concentration of B and of MB in the solution, maximize the contact between the Congo red and particles M and B, minimize the contacts between. I would, if I read this, just reading it, I'm going to say that the reason why you would shake it would be to maximize the contact between something. You wouldn't be increasing, decreasing concentration, I don't think, by shaking it. I have to read. And you wouldn't minimize contact by shaking it, right? Shaking it means you maximize contact. You make stuff mix together and hit each other. So I bet you it's H just by just thinking about it. But why was the flash shaken? Let's see, when they talked about the flash being shaken. Let's see what this is about, though. Dyes such as Congo are often found in industrial wastewater and must be removed from the water before the water can be discharged. How much cargo red would be removed from a solution by binding to particles? So we want to bind the cargo red to the bentene or MB. So yeah, if you shake it, that will make it bind. Uh, the flask was sealed and shaken at a speed of 200 revolutions per minute. The contents of each flask was filtered to remove all solid material. Right, so that's why you would shake it so it binds with these different B and MBs, maximize the contact between the B and MB so it binds to them, and that takes the red out of the water. So yeah, it would be H. A 19. Let me just make sure that was 18. Science, 18. Yes, 8. I thought so. I just want to check, make sure. All right, 19. Suppose that in an additional trial of experiment three, a shaking time of 100 minutes had been tested. The percent of CR removed by HB in this trial will most likely have been between. So suppose, meaning this didn't happen, in an additional trial of experiment three, a shaking time of 100 minutes had been tested. Percent CR removed by MB is most likely again. So let's see where would 100 minutes fit in experiment three? So experiment three is here, so figure three. Um, oh no, 100 minutes would be between here. Let's see how this goes. 90, 100, 120, 120. So 100 minutes would be there, and it wasn't done, but it would be just after there. So which one are we looking at? Are we looking at the B or the MB for that question? Uh, Shaking time of doing 7 tested the percent of CR removed by MB. MB would be the dark squares. 100 minutes would be just past this one because this is 90 minutes, so just past 90 is 100. So you would be between 80% to a little bit over 80%, but not quite 90, right? It's 80. I think this goes about 5, 85, 90, 95, 100, right? It's going about 5. So I'd say probably between 80, 85%. Yeah, between 80 and 90%, that would be D. Yeah. All right, number 20, in experiment two, the percent of CR removed by B from the neutral Congo red solution was closest to which of the following? Experiment two, we're looking for the percent of CR removed by B from the neutral Congo red solution. Experiment two, percent of CR removed by B from the neutral. And it emphasized neutral or neutral. Okay, so what's a neutral solution? This requires background information. I do know this though. A pH neutral is 7. 7 is neutral. It's in the middle. Anything lower than 7 is acidic. Anything higher than 7 is considered base or alkaline. So 7 is neutral. So you do need to know background information. What is a neutral pH? And neutral MB would be a little bit lower than 100, so about 95% was removed. But it was close to 100. It was closest to 100. Yeah, it was close to 100. But all of, well, this one's close to 90, 85, 90. So I was just thinking, so 90 would be if it were 9 or 10, but we know neutral is 7, which is closer to 100. Yeah. So that would be J. All right, 21. Based on the results of experiment 2 and 3, the percent CR move will likely be greatest for which of the following combinations of pH and shaking time? All right, based on experiments 2 and 3. So which pH would have the percent CR move will be the greatest? pH, experiment 2. The greatest pH would be the lowest for percent removal because we see lower pHs have, whether it's MB or B, lower pHs have a higher percentage removal. So a pH of 5, definitely. So C and D are gone. And what about shaking time? We know high shaking time or low shaking time. We see that as you increase shaking time, the percent removed increases. So we want a higher shaking time. So it'd be B. Low pH 5, lower than 10. Shaking time 240, B, choice B. Based on figure 2 and additional information in the passage, how many trials were performed in experiment 2? Based on figure 2 and additional information in the passage, how many trials? How many trials were performed in experiment 2? In each trial, the percent CR removed was determined for either B or MB at each of 6 pH levels. 6. In each trial, the PR removal determined for both B and E at 1 of 6. At 1 of 6. No, it was at each of 6. But figure experiment 2, you see that because the dot is at each of 6. 1, 2, 3, 4, 5, 6. They performed, so the dot means we took a measurement, right? So we took a measurement at each of 6 pH levels. So I'm looking at the reasons, right? Before I looked. So at each of six, so the reason so far for F is right. In each trial, the CR removed was determined for both B and B at one of six. No, it wasn't at one of six. It was at each of six. Let's look at H. In each trial, the percent CR removed was determined for either B or one at one of six. No, it wasn't one of six. So G and H are wrong. In each trial, the percent CR removed was determined for either B or MB or Congo red at one of six. No. It's in each trial, the CR removal is determined for either B or MB at each of six pH values. That is true as F. I can get F without even understanding this experiment or what the question is asking, right? Um, you see that? And I'm not counting how many trials. Wait, they said 18 trials in each trial. The percent CR removed was determined for either MB or if the percent CR removed was not determined for Congo red. It would just B or MB. So that's why J is wrong. And it wasn't at one of six values. Wait, it could be 12 though. In each trial, the percent CR removed was determined for either B or MB at one of six pH value. I think it is actually H. Because it wasn't, the question says, based on figure two and additional information in the passage, how many trials were performed in experiment two? It wasn't two trials, it was 12. In each trial, the CR removed was determined for either B or MB at each of six. It could be F or H, 12 in each trial, because you could say two times what? Six pHs, that's 12, and then 12, one of six. That could be either one. Hmm. Let's see. What is figured that in all trials, the mass of B and B was, and the shaking time was 360 minutes. From trial to trial, the pH of the Congo red solution was varied. So from trial to trial, the pH was varied. That means each one of these represents a trial. So it was 12 then. I just wanted to see if they said anything else. That is shaken. Yeah, it was in all trials, the massive MV was, and the shaking time was 360 from trial to trial. So trial to trial, the pH of the Congo resolution was varied. So the different pHs. So each trial had a different pH. So it wasn't two trials, it was 12 trials. It was H. And in each trial, the remove was determined for either B or A at one of six pH values. That's correct. It was H. Yeah. So I had to do a little bit of work with that. All right, 23. Consider the description of experiment one and the percent CR removed by MB in the zero point 0.2 gram trial of experiment one. So let's look at that. Consider the description of experiment one and the percent CR removed by MB in the zero point 0.2 gram trial. So zero point 0.2 grams here, percent removal there for which one was it, B or MB? MB should be 100%. So all the CR is removed and the mass of B or MB, I think the mass of MB was 0.2. Um, the concentration of Congo red that remained in the solution when the shaking ended was approximately zero. Because they said 100% of the CR was removed when the mass of the MB was 0.20 grams. In our trials, the pH of the Congo resolution was the same, and the shaking time was 360 from trial to trial. The mass was varied. How'd they vary the mass? I guess they just added more or less. I was wondering if the shaking increased the mass. No, I didn't say that. I just wondered. Yeah, so that would be 22 would have been zero because 100% for the zero point 0.2 gram trial, 100% of the CR was removed by MB. So if you removed it all, right, but zero point 0.2 grams of MB here, 100% was removed. That means this removed, CR removed was 100. That means no CR remained. No Congo red remained. So 23 would be A. Just check it just to make sure. Three. Yeah, I thought so. All right, let's see. Well, we almost an hour in on this one. All right. We only about halfway through. Okay, wow, that's another conflicting viewpoints in this science. So I guess you do have to read. I think we're going to take a break here and we'll resume the rest of them. So I think we got to do these in two parts when these are, as long as these are, or do I want to keep going? Yeah, let's take a break. Take a break.